Okay, so continuing, before going ahead in the relations topic, let's go back and let's discuss about some unique and certain kinds of sets and also events. They are mostly used in probability chapter, but if we understand here, then we'll be able to solve them easily and understand when we'll be solving probability questions. So these are some type of sets, exhaustive sets, in which are both of the sets or any given sets are completely occupying the universal set. As you know, this is the Venn diagram, and this rectangular box represents the universal set. And here the set A and B collectively occupying all of the universal set. So the union set of A and B is equal to universal set. Okay, this is universal set. That's why we are calling these sets as exhaustive sets. Exhaustive. They have exhausted all the universal set. Okay. What is universal set? Universal set is the superset include or superset of all the sets which we are discussing about. Okay. Any doubt? Understanding exhaustive sets?
No doubt, sir.
Okay. Non-exhaustive sets or events. Events we will call certain events in context to probability. So we will understand this term later in probability. Discussing about non-exhaustive sets, those sets which do not occupy collectively do not occupy all of the universal set. Here, A and B were collectively occupying all of the universal set, but it is not the case here. That's why we are calling them as non-exhaustive sets. Any doubts?
No
No,
doubt, sir.
let's move ahead. Yeah, let's discuss the first one, mutually exclusive sets. Mutually exclusive sets means they are disjoint sets. Disjoint sets. Yeah, means that if there are like A and B sets, the intersection of these sets is a null set. This is a phi symbol used for representing a null set. Discussing about non-mutually exclusive sets, those sets which are intersecting each other, and the intersecting set of both the sets is non-empty. There are certain elements in that. Okay, so in this case, we will call these two sets as non-mutually exclusive sets. Okay, exclusive means that they are like very unique from each other. They don't have any in common in between. Mutually, we compare them to each other. Okay, let's now. Any doubt? If any doubt, me ask. I'll repeat.
No doubt, sir.
Okay, discussing about collectively exhaustive sets means if there are okay. If there are sets which are occupying the universal set collectively, means they are the similar what we have discussed earlier here, exhaustive sets. Now the difference in this and this is they are mutually exclusive also and collectively exhaustive also. Mutually exclusive means neither of the set is intersecting with each other. In this case, A, B, C, D are all disjoint sets with respect to each other. But when we discuss about this particular set of sets, then here A and B are intersecting at certain point. That's why they are not mutually exclusive. But yes, they are occupying all of the space in universal set. So we'll call them as collectively exhaustive. Any doubt?
No
No,
doubt,
sir.
sir.
So here, tell me if is is A and B are A and B are mutually exclusive or not? Mutually exclusive or not? A and B. Exclusivity means they are not intersecting with each other.
Yes, sir, they are mutually exclusive.
Yes, they are mutually exclusive because they are not intersecting with each. Is it the case here also?
Yes, sir, neither
Yes.
of them are intersecting.
Yes, good. Okay, so we have discussed this whole earlier in the class. Since we were discussing about relations. So for Caesar, let me repeat that you must be aware about, like, let's say there are two non-empty sets A and B, and if we have to take the product of these two sets, then we call it as a Cartesian product. And in Cartesian product, this is a set which will be coming out after the product, and it will be having certain elements where A will be belonging, where for all A belonging to set A and B element belonging from set B. This is the Cartesian product set. And if we take any subset from this particular set, then we call it as a relation. Let A and B are two an empty set, then a relation from A to B is a subset of A and B. And here, as you must be aware, that B cross A is equal to A cross B. Is it so, Sirja? We are talking about Cartesian product between two sets that are A and A and B are not equal sets. Is it true or false? You may answer. Even if you give no wrong answer, that's no problem. I'll be explaining. If you give right answer, then I won't be explaining. That's the only difference. Anyone? True or false? We're discussing about Cartesian product of
No,
sets
sir.
A and B. No, yes, because the B in B and the Cartesian product of B and A will be including set will be elements including elements like B and A for all B belonging to set B and A belonging to set A. So they are reversed. So these are ordered pairs. These two ordered pairs are not equal. That's why they are not equal. So the commutative property is not hold true in case of Cartesian product. So if we take any subset from this particular Cartesian product set, then it is known as a relation. Okay, and domain will be simply the first element of that particular relation. That will be the domain of that particular relation. The second element or the second element of that particular relation will be the range of that particular relation. And when we talk about codomain, so simply the complete set B will be known as the codomain of relation. Any doubt?
No,
Any
sir.
doubt?
No, sir.
Discussing about empty relations which will be having no element in that. Universal relation is a relation means when we are taking relation from A to A only. Like if we were discussing about taking a subset from this particular Cartesian product. If we take this particular Cartesian product, discussion of this particular Cartesian product is going on, and when, instead of taking its subset, we take all of this particular set and find out its relation. है ना? Then it will be known as a universal relation, basically the Cartesian product of a set with the set on itself. Okay? Any doubt? It will be more clear when we will discuss questions. Clear?
Yes, sir.
An identity relation is a kind of relation in which all the elements, if there is a particular set which we are discussing about, and each and every element of the set is repeated twice in this format, and no other elements in that particular relation is available, then we'll call it as a identity relation. Any doubt? As in the given example, also 1, 2, 3 are the elements in the set. Then in relation, if 1, 1, 2, 2, 3, 3 must be having and nothing else must be there. Then we'll call it as an identity relation. Okay. Any doubt?
No, sir.
No, sir.
Inverse relation is basically we inverse the first and second element, and so let me write if there was a relation like this. So we were calling this as a domain set of first elements. So domain will be set of first elements, there is 1, 2, and 3. Range will be set of second elements 1, 4, and 9. So if we have to find out inverse relation, we will simply do one thing. We'll reverse the first and second elements. Okay, so 1, 1 becomes 1, 1, 2, 4 becomes 4, 2, and 3, 9 becomes 9, 3. And now the domain of R inverse becomes set of first elements. That's 1, 4, and 9. Range of R inverse becomes set of second element, that is 1, 2, and 3. So now if we see the domain of the R becomes the range of R inverse, and the range of R becomes domain of R inverse. So it's simple, very simple, inverse relation. Any doubt?
No doubt, sir.
Okay. So if there is a set 1, 2, 3, R and its relation is given, the most probably the relation is on A cross A itself. Then the domain and range of R inverse. We have to find out the domain and inverse range of R inverse. First, let's find the domain of R. So its domain is 1, 2, and 3. Yeah, 1, 2, and 3. Do you agree its domain is 1, 2, and 3? What is its range? Please tell me. Range of R.
2, 2, 1.
2, 2, 1. So we'll write 2, 2, 1. We do not repeat elements in set. So 2,
2,
1.
1.
Yeah, 1, 2, or 2, 1 is similar. So now we know domain and range of R. So for finding the R inverse, this will become its range, and this will become its domain of R inverse. Okay, this will become the domain of, and this will become the range of R inverse. Okay, so this is the range. So we have to find out the domain first. Domain of R inverse is 2, 1. So this one, yes. And the range of R inverse is 1, 2, 3, 1, 2, 3. And no other option is there. So option A will be your correct answer. Correct answer. Clear? Any doubt? And there is a mistake in this question. Can you spot? Option A and option B are similar. Because in sets, when we write sets, order of element does not matter. Like A, E, I, O, U. If there's a set, B set is like O, U, I, A, E. So A and B are equal sets because the order of elements doesn't matter. So one mistake in the question. Okay, let's discuss about various type of relation. Any doubt? Any doubt till the discussion that we had?
No, sir.
And please cooperate with my tutti frutti English. Broken English. Okay. Various types of relation. First, reflexive relation. A relation R on a set A is said to be a reflexive relation if if there is an element A in the relation for all A belonging to R. So it means that if there is any element A present in the relation, then it must be the case that of that particular element, this particular element is also must be present in the relation itself. So it's like saying, let me give you examples. Here I'm not in my book. Okay, so let's understand from the definition itself. That let's show the definition first. So if there is a relation on set A simply, and on A, and if relation on set A means set A cross A, okay, yani we are taking a relation on set A into the Cartesian product of A itself, and it might happen in others also. Let's not make the definition very generic, very specific in nature. So let's write it. If let's say the if condition first. So if there is any element belonging to relation, any element, how it will be belonging in the relation in forms like AB. Means if there is AB written in the relation, then it must be the scenario that A and A should be in the relation and B should be in the relation, then the relation will be known as reflexive relation. Means if there is like 1, 2, 3 present in the relation, then the R is not reflexive because 1 is there, 2 is there, and 3 is there. But it should be the case then, it should be the case that 1, 1, 2, 2, and 3, 3 all must be present in the relation. Then only that particular given relation will be known as reflexive. Uh, you will be only able to understand after giving examples. Let me take a set. Let's take a let's say there's a relation x less than y. So and it is on set A and B. Set A is 1, 2, and 3. Set B is 3, 4, and 5. Okay, so and we have to take a relation from A to B. So the first element must be from, let me write the relation in set builder form, x, y, such that x, uh, x must be less than y for all x belonging to A set and y belonging to set B. Now we write the relations element, this particular set's element. So x must be less than y. So 1 is less than 3, so we can write it. 1 is less than 4, we may write it. 1 is less than 5, we may write it. And no other element is there. 2 is less than 3, yes. 2 is less than 4, yes. 2 is less than 5, yes. 3 is less than 3, no, it's not the case. 3 is less than 4, yes. 3 is less than 5, yes. Okay, so these are the element only. So now if we see in this particular relation, if there is 1 and 3 in this, like all the elements are of nature, are having different elements. Like there is no 1, 1 present, there is no 2, 2 present, there is no 3, 3 present in the given relation. That's why this given relation is not reflexive, right? Given R is not reflexive relation. Any doubts?
No doubt, sir.
We will take more examples here. This is very easy. Symmetric relation. It is simple that if a element xy is belonging in the relation, then yx must be present in the relation for calling the relation as symmetric relation. If there is, and we don't have to discuss about the parent set in this particular relation. If we do not care whatever elements are present in the set or not. We just care about the elements which are there in the relation. Okay, so if I'm writing a relation like 1, 1, 1, 2, 2, 1, and 3, 1. So for now let's check whether whether the given relation is reflexible. So 1, 1 is there, that's good. 1, 2 is there. So there must be 2, 2 here. So is there 2, 2? No. So the given relation is not reflexive. So reflexive name. let's discuss about symmetric. 1 1 is there. So is 1 1 there? Yes, 1 1 is there. So is 1 2 if 1 2 is here, then 2 1 is here or not? Yes, 2 1 is here. If 2 1 is here, 1 2 is there or not? Yes, 1 2 is there. If 3 1 is here, is 1 3 here? No. So that's why the symmetric relation, this particular relation is not symmetric. Any doubts? It is very simple that if, let me write its definition as square box only. If AB, this particular element is in the is in the relation given, and BA is also in the relation, then R is symmetric relation. Any doubt?
No doubt, sir.
Okay. Let's discuss about anti-symmetric relation. It is simple that if xy is there, whatever is here, if AB is present in the relation and BA is not present in the relation, for some element, its reverse, its symmetric element is not present, then we may call the given relation as anti-symmetric relation. We call R as anti-symmetric relation. Any doubts?
No, sir.
No, sir.
For this. So if there is a set A and given relation is 1 2 1 3 1 1. So if 1 2 is there, is 2 1 there? No. So it's not symmetric. That's why it's anti-symmetric. If R2 is here 1 2, so is 2 1 here? No. So that's why it is anti-symmetric, R1 and R2. Let's read the definition also. A relation R on a set A is said to be an anti-symmetric relation if AB belonging to relation R and BA belonging to relation R. It suggests that A and B are equal. Okay. Thus, if A is not equals to B, then A may be related to B or B may be related to A, but never both. It means that it may be the case that 1 1 may be present in the relation. We don't have any problem with that. But if there is 1 2 and 2 then 2 1 must not be present, then we may call the given relation as anti-symmetric. Okay. Any doubt? Any doubt?
No, sir, this is clear.
Let's discuss about transitive relation. It's the most simple relation. So it's simple that if AB element is present in the relation and BC element is present in the relation and AC element is present in the relation, then we may call the given relation as transitive relation. Means if there is like element, let's discuss about this relation itself. If there is 1 3 present and 3 4 present, so this element, this is A, this is B, and this is B, and this is C. So if there is 1 3 and 3 4 present, then there must be an element 1 4 in the relation. Then only we are going to call it as transitive relation. Is 1 4 present here? Yes, 1 4 is there. If there is 1 4 and no, and there's no element, there's no particular element which have its first element as 4. No, there is not such. So let's discuss about this. If there is 1 5, no any elements having 5 as first element. Okay, leave it. 1 5, there's no other element having 5 as the first element. 2 3. So is there any element having 3? Yes, this is the element having 3 as first. So 2, 3, 3, 4, the 2, 4 must be an element. Yes, it is the case. Okay. Till now our condition is satisfied. Wherever our condition fails, we'll declare the relation as not transitive. Okay. 2, 3 and 3, 4. So 2, 4 is there. Okay, no problem. 2, 4 is there. Any element starting with 4? No. 2, 5, any element starting with 5? No. 3, 4, any element starting with 4? No. 3, 5, any element starting with 5? No. So we have checked all the elements, and yes, our condition is satisfied all the time. That's why we'll declare this relation as transitive relation. Any doubt?
No, sir.
It was very easy, but just you have to be very sure while checking. There's also an example given. So let A set 1, 2, 3 and the relation 1, 2, 2, 1 and 1, 1. So first of all, let's check whether the relation is reflexive or not, symmetric or not, transitive or not. For sorry, for checking reflexive, there must be 1, 1, 2, 2 and 3, 3. 1, 1 is there, but 2, 2 and 3, 3 are not here. So that's why I will call this relation as not reflexive. Talking about symmetric, so we don't have any matlab, we don't have any interest in seeing the set. So let's discuss about the relation itself. If 1, 2 is there 2, 1 present? Please answer. If 1, 2 is present, is there any 2, 1 present in this relation? Come on, it's there. Yes, it is here. So 1, 2 is there, then 2, 1 is here. Okay. 1, 2 is here and 2, 1 is here. No problem. 2, 1 is here, 1, 2 is there. No problem. 1, 1 is here, 1, 1 is here. So this is symmetric. Yes. Discussing about its transitiveness. If 1, 2 is there and 2, 1 is here, so A being 1, 2, 2, 1 and 1, 1. Okay. And this is the set of relation. If 1, 2 is there, 2, 1 is there. So this is A, B, B, C. Okay, then 1, 1 must be here. Okay, this is satisfying. Let's check about second element. If 2, 1 is here, is there any element having 1 as starting? Yes, there is. So if 2, 1 is here and 1, 2 is here, so what we are discussing now is A, B and B, C. So if 2, 1 is here and 1, 2 is here, is there any element 2, 2 in the relation? Please answer. If AB is here, BC is here, then AC must AC, which is A2 and C is 2. Then this particular element must also be present in R. Is that the case? Is there any element 2, 2?
No, sir.
No, that's why this is not transitive. R is not transitive since R includes 2, 1 and 1, 2, but there is no 2, 2. That's why this particular relation is not transitive. You have to just look for the condition, look where the condition is failing. If it is failing, then only we'll declare that particular given relation as not uh, transitive. Okay. And if our condition is not failing anywhere, then definitely it is transitive relation. Any doubt? There are a lot of questions asked on these three: reflexive, symmetric, and transitive. And if we collectively talk about all these three, if there is a relation like Eid ka Chand, the moon of Eid, if there is any relation on a set A, said to be an equivalence relation when the given relation is reflexive, when the given relation is symmetric and transitive as well, then we may call the given relation as equivalence relation. Now you may confuse that this given set is 1, 2, 3. Now please tell me whether this particular relation is equivalence or not. And even you have 10 seconds. Okay.
No,
So
sir.
yes, it is not. This is reflexive or not?
Yes, sir.
This is symmetric or not?
No, sir.
This is not symmetric. Why?
One. A, comma, B. A, comma, B.
If 1 1 is 1 1 here? Yes, of course it's
Yes, sir.
here. If 2 2 is here, is 2 2 here? Yes, it is
Yes,
here.
sir.
Symmetric is.
It's
Then is
symmetric.
it transitive?
No, sir.
No.
No.
So it's debatable. Okay. So whenever it is, I have observed the previous year question and their answer keys that whenever this kind of relation is asked in UPSC and the exam, then the correct answer is considered as it is a reflexive relation. This is an identity relation. So this is known as a reflexive relation, and you should mark this option. Okay, that's all. Okay, any doubt?
No, sir.
So let's discuss about this relation. So the relation x less than y on set of all real numbers. Take it as all real numbers set of all real numbers. So if we'll map out, so we cannot like uh, write all the elements of this given relation, right? Why? Because real numbers are infinite. So we'll just discuss about relations directly, and we'll try to find, as we know, what will be the numbers like 2, 3 must. Oh no, 2, 3 no. So real number, this particular relation will be having infinite number of sets. So we can write some examples like -3 and -4, minus +3 and +2. Am I right? Wherever I'm wrong, please stop me. And minus zero point -0.5 and -1 and 5 and 4 and infinite number of elements. So these are some examples of elements which we have taken. And other examples are like, if we have to write all the elements in the set, we will not be able to do so because it's an infinite set. So let's discuss about reflexive relation first. So if there is a number like 3, so can we write 3 3 in the set here? Can we write? Can any number be equal here? Like if the relation is this, well, can this be true? Because then only we will be able to write x in the relation. Is this true? Is x greater than x? Is any number greater than it itself?
No, sir.
No, it's not true. It's not true. That's why this XX elements will not be present in the relation, and the given relation is not a reflexive relation. Okay, let's discuss about symmetric relation. So if x is greater than y, then can we write y is greater than x? If a number is greater than other number, like 2 is greater than 1, then maybe write 1 is greater than 2. Then
No,
only we'll be able to write in the relation. Can we do that?
no, sir.
That's why this given relation is not symmetric. It's antisymmetric. Okay. So let's check once more for the transitive relation. Okay. Good. Now discussing about transitive relation. So if we write that if there is a number greater than second number, the second number is greater than third number. So according to this, xy is an element of relation, yz is an element of relation. So can we write in this case that x is greater than z? Let's take one example like 4 is greater than 3, 3 is greater than 2. So maybe write 4 is greater than 2. Is it possible?
Mm, yes, sir.
Yes, it is. It is. So what we will write that xz will also be belonging to the relation. That's why we will call this particular relation as transitive. But let's take one more example. Maybe we can fail for sometimes. So let's discuss for negative numbers. -2, okay. -1 is greater than -2. -2 is greater than, okay, this could go. Yeah. 0 is greater than -1. -1 is greater than -2. -2 is greater than. Can we write from this? Is 0 is greater than -2? Yes, we can. Yes, we can. So this is a transitive relation. Let's mark the option number A. Why not antisymmetric? Why not antisymmetric? Antisymmetric relations must be having a same element in them. Like if we go back to the definition. So a relational set A is said to be an antisymmetric relation if AB belonging to the relation and BA belonging to the relation, then it means that AB are equal. Okay, thus if A and B are not equal, then A may be related to B, that A may be, this can be the case, or B may be related to A, that this may be the case. Array, bhai. Let me save the file first. It is also that reflexive, symmetric, and transitive, they are the like main options. Okay, so it's debatable. Antisymmetric, this can also be antisymmetric because it's not symmetric anywhere. But we will consider transitive as a right option. Let's see on the question in the example solution itself. This is not symmetric, but still the answer is not marked as antisymmetric. Maybe it can be a problem with the author who have written this book. But in when you will solve NDA question also, please first check RST, reflexive, symmetric, and transitive, and then go to antisymmetric. Prioritize these as answers. Okay. Any doubt?
No, sir.
Let's discuss about composition of relations. If R is a relation from A to B, and S is a relation from B to C, then S of R is a composition relation of S and R from A to C. And for making a composition relation, the like from SOR, then it will, the composition relation SOR will only exist if R is a set from A to B, and like basically this particular set is common, should be common between these two sets, and then S of R relation, that composition relation will be exist. We'll take more example, you'll be able to understand. So this is taken from NISO Academy YouTube video. Let A, B, and C be three sets. Suppose R is a relation from A to B, S is a relation from B to C. The composite of R and S is denoted by S of R. It's a binary relation from A to C. consisting of ordered pair AC, where A belonging to set A, C belonging to set C. Also B belonging to set B, such that AB belongs to the relation R and BC belongs to the set C. Sorry, relations S. So first of all, understand the gist here that it must be the case when we are taking a composition of R and S, then this particular element, this particular set must be common in between these two, and we will be writing it as S first, and O, and then R. This is B to C, this is A to B. So this element must be common for writing. Then only there will be some composite relation. If R and S are relations from A to B and C to D, then SOR is not defined unless B is equals to C. Unless this set is equals to this. Let's take an example. What is the composited relation? We have basically first map when we have to find out SOR. So first map relation R. How we will map the relation R? So the given relation is 1. So relation R is this from A to B. So from A to B, let's do set A and then B. Same is done here also. So from set A to B, this is a relation R, and this is a relation from B to C, S. Okay, after doing so, what we will do, okay, basically this is set A, B, and C. The relation R, this is S. Now we'll map the relation how 1, 3 is there. So first write for all the set A, B, and C, and then let's see on the relation R. 1, 3 is there, then map 1 to 3. Where's 3? 1 to 3. 1, 4 is there, from 1 map 1 to 4. 1, 5 map 1 to 5. Similarly, others also. Similarly, what is the set? What is the relation S? It is 3, 1, 3, 2, 3, 3, 4, 3. So 3 to 1, 3 to 2, 3 to 3, and 4 to 3, 4 to 3, and 4 to 4, 4 to 4 here. So now we have mapped all the relation R and S. Now to finding SOR, we'll go from set A to C. How we will go? We will take paths like 1, 2, 3, then 1. So 1, 1 will be written. Then 1, 2, 3, and 2. So 3 will be ignored. The B set will be completely ignored. It is just a path. 1, 2, 3, and 1, then 2, 2. So 1, 2, 1, 2. 1, 2, 3, and then 2, 3. 1, 3. 1, 2, 3, and then 2, 4. Is it going to 4? No. So the story of one ants here. Let's discuss about no. The story of 1 and 3 ants here. Now discuss from 1 to 4 and 4 to 3. So 1, 3. Yes, it is already there. So we will not write it twice. 1 to 4 and 4 to 4. So 1, 4. Yes, write it. Then 1 to 4 and there's no other path to go ahead. Okay, the story of 1 and 4 ends here. 1, 5. 1 to 5 and 5 is not going anywhere. So story ends here. So let's now talk about 2. 2 to 1, 2 to 3 and 2 to 1. So 2, 1 should be there. Okay, 2, 1. 2 to 3 and 3 to 2. So 2, 2 should be there. 2 to 3 and 3 to 3. So 2, 3 must be there. 2 to 3 and there's no other path. Okay, and 2 to 4 and 4 to 3. So 2 to, okay, 2 is not connected to 4. No, 2 is not connected to 5. Leave it then. 3 is connected to only 3. So 3 to 3 and 1. So 3, 1 must be here. Okay, written. 3 to 3 and 3 to 2. So 3, 2 should be here. Okay. 3 to 3 and 3 to 3. So 3, 3 should be here. And there's no other connection of 3 here. Okay, so it is like this. That's how we'll be finding the composition relation. We'll first map it all A, B, C, and RS. If we have to find out SOR, then we'll be only able to find it. Any doubts?
No, sir.
Okay, let me take an example and write it by myself. If there is a relation for A to B, so there is a relation from set A to set B, and such that 1, 2, 3, 4, 1, 3, 5 from set A to B, such that AB belonging to relation R, and if A is less than B, so the first element should be less than this. So 1 is less than 1? No. 1 is less than 3, so we'll map it. 1 is less than 5, we'll map it. 2 is less than 1? No. 2 is not less than 2 is less than 3? Yes. 2 is less than 5? Yes. 3 is less than 3? No. 3 is less than 1? No. 3 is less than 5? Yes. 4 is less than 5? Yes. Because this was the relation where A must be smaller than B. A belonging to set A and B belonging to set B. So this is our relation. Let's write R as 1, 3 and 1, 5 and 2, 3, 2, 5, 3, 3 and 3, 5 and 4, 5. So 1, 2, 3, 4, 7. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6. There are only 6. 4 and 3. Have I repeated anything? 1, 3. So how have I written 3, 3? This is Battamiji. Okay. 2 is to 5. 2 is to 3. 3 is to 5 only. Okay. So this is our relation. And now we have to find R of R minus. Like R of R minus. R inverse basically. So let's map R inverse. R inverse is simply 3, 1, 5, 1, 3, 2. We are inversing. And 5, 2. And 5, 3, and 5, 4. This is R inverse. Now R is from A to B and R inverse is from B to A. We have to find R of R inverse. And for that, if this is B to A and this is A to B, this element must be equal. Going back, when SOR R was from A to B and S was the set from R is a relation from A to B and S is a relation from B to C. So these two sets must be equal. And here also, are they equal? Yes, they are equal. So we'll be able to find out them. So for finding ROR inverse, we'll map out R inverse first. R inverse is from B set to A set. And then we will write the R from A to B. So let's take help from here and save our time. Okay, let's bring it here. Okay, any doubt, anyone? Any doubt? Are you with me? Is everything clear till now?
Yes, sir.
Space. So A to B is mapped relation R inverse is 3 2. So let's write the B set first. B set is what is the B set? 1 3 5. So now let's map 3 to 1, 3 to 1, 5 to 1, 5 to 1, 3 to 2, and 5 to 2, 5 to 3, 5 to 4. Okay, this was only. So for finding ROR inverse, we'll go from set B to P. So ROR inverse is a relation on B to B only. So we'll go from B to B here to here. So this is R inverse, this is R. Finding ROR inverse, we'll go from here to here. So 3 to 1 and 1 to 3. So 3 should be there. 3 to 1 and 1 to 3. 3 to 1 and 1 to 5. 3, 5 should be there. 3 to 1 and 1 to 5. And there's no other way. 3 to 2 and 2 to 3. So 3, 3 should be there, which is already there. 3 to 2 and 3 to 5. 3 to 5 is already there. There's no other way then. Okay. So let's come into 5. 5 to 1 and 5 to 3. So 5, 3 should be there. 5 to 1 and 5 to 5. So 5, 5 should be there. And 5 to 1 and 5. So there's no other option. 5 to 2 and 2 to 3. So 5, 3 is already there. 5 to 2 and 2 to 5. 5, 5 is already there. 5 to 4 and 4 to 5. 5, 5 is already there. There's no other element making up. There, this is the answer. Okay, and this is the easiest way to find out ROR inverse. Let's check our answer. Oh, there's no solution given. This is the correct answer. I remember. Any doubt, or should I explain it again? Should I do it again? You may ask. No problem. Should I repeat it?
No, sir. Clear.
Here. Okay. So this is all about today's class. We'll discuss function in tomorrow's class. Any other doubt?
No, sir.
Sir, no doubts.
Okay.